Thanks. Okay, thanks for staying up late to hear this. So this is going to be very much an overview, just a flavor of some of the ideas you've heard, maybe pull together some of the things you've learned in the last week and a half or possibly elsewhere. It will perhaps be not so rich in new information for many of you, but the idea is to just sort of relax and take it easy. So let's start. So a possible summary of the things I might discuss are these various things, and I'll touch on them. That seems like a lot of topics to cover in 1 hour, and but I'll be touching only briefly on some of these, and you'll have seen some of the themes before. I just want to pull them together and just take you through some of the things people are thinking about and things people are excited about. So, given that we're going at a somewhat leisurely pace, I don't want this to be too formal, so if a burning question occurs to you, just stop me and I'll see if I can answer it. So, let's actually start out with a little bit of history. So let's think about the early days of particle physics. Unfortunately, something's wrong with Netscape on my computer. It's not rendering images as fast as it should, so I apologize for that. So, well, how do we get to particle physics? Well, we look at something like a glass of water, anything. We look closely, and we'll find molecules which are made of atoms, which are in turn made of protons, neutrons, and electrons. And you look closely at one of these things, and you know the story. You see with a magnifying glass, for example, hydrogen. You can look deeply inside with some kind of magnifying glass. And that, of course, is meant to be a caricature of the kind of magnifying glass you would really use. But I think it's well understood. Actually, you'll be hearing about some of those magnifying glasses in the collider physics lectures next week. But the important thing is that these things are glued together, the electrons to the rest of the atom, for example, by essentially the electromagnetic force. So let's actually spend a little time reminding ourselves of some of the things we know. For example, I can take an electron-positron pair. It's a little distant, so let's look a little bit closer. There it is. And I can do, for example, draw some flux lines between an electron and a positron. Just to remind you, of course, the positron is just like the electron, except it's its antiparticle, so it has a positive charge. And these are the sorts of flux lines you may draw for the electric field. For this configuration. And if you separated them out, you imagine you draw flux lines looking something like that, and you can continue this process. You separate them out, and then you might have a configuration that looks something like this. And you can see that ultimately, if I go far away enough, separate these guys far away enough, you can see, for example, if I were to attempt to block out part of this, that if you didn't know that the other thing was there behind me, you might think that this is just a free electron and the lines are stretching off to infinity. And that gets better and better as these guys stretch far away. And that is an important point. The force, for example, as you know, Coulomb's law goes something like that, and it falls off. And those field lines fall off, and that's a pictorial way of thinking about this. You know this. Why am I telling you this easy stuff? Well, because it illustrates an important thing. The strong nuclear force which glues together the quarks inside, say, the proton, actually operates somewhat differently. So let's actually start with a quark-antiquark pair. And the sort of flux lines I draw would sort of look like this. So the flux lines now are not electric flux lines, they're color flux lines. Remember, these guys are using the strong nuclear force to interact, but I can draw flux lines. And so I can try and separate that quark-antiquark pair. And I separate them, and you see that, in fact, the flux lines stretch out a little like that. They actually don't want to sort of spread out. They want to go as quickly as possible to the other guy. And so they sort of form a tube. And you can try and separate them further, and that tube just gets more stretched out. At some point, actually, the amount of energy you've stored in that gets to a certain point, and it becomes energetically favorable to snap, to actually create another quark-antiquark pair and sort of break the tube, and then they stretch out between them like that. And that's sort of interesting. That might be suggestive of something. This is real physics I'm discussing. I haven't made anything up yet. This is how we're supposed to think about these forces. And anyway, the point is that the force behaves very differently from the force law that we learned about from the electromagnetic case. It becomes actually harder and harder it becomes impossible to separate one of these guys and make it a free quark. And that is, at least schematically, some of the origins of the concept of quark confinement, which you've heard about. So among the questions in the late 60s were, what kind of physical theories underlie that kind of interaction? It has to, whatever it must do, it must explain this confinement phenomenon. And we'd also like to explain all the very many hadronic particles that were being discovered at the time, where hadrons are baryons and mesons. Baryons, remember, made of 3 quarks, and mesons made of 2. And actually, the notebooks at the time were largely empty of good ideas. Well, yeah, that's a fair point. And so the question is, what do I write in my actual notebook to model this phenomenon? So, as you probably guessed, much of what you saw for the behavior of the strong force reminds you of sort of stringy behavior. It's a little bit like stretching something out, and it's a string, and then it snaps if you stretch it too much, and you never ever get an isolated end of string because there's always another end. And so that's very suggestive. And string theory, in its first incarnation, was trying to make that idea, make a real model out of that idea. So inspired by that previous picture, and lots of theoretical successes. It wasn't just drawing pictures, but actual real calculations. The proposal is that quarks are maybe the ends of some string, and you have a quark-antiquark pair, for example, and they are the ends of some string, and then the sort of big fluffy thing that you look at sort of far away, you don't realize it's a string, that's what you think of as a meson. And actually, then the idea is that you can explain how mesons might decay into other mesons or things like that by the string snapping, joining and reconnecting in various ways. And actually, let me just go over here. You can see, in fact, that this is a cartoon of some of the things that people actually computed. You can study, perhaps Melanie mentioned that today, I'm not sure. You can actually study the spectrum of a relativistic string as a model of the mesons, and you actually get a characteristic spectrum in string theory. If you plot the mass squared against the spin of the various resonances, the various things that show up in the string spectrum, they fall on these things called Regge trajectories, straight lines with a very characteristic slope, characteristic of the string. And actually, experimentally, this was also observed, so that was actually very encouraging. And there are a few embarrassing features to the rest of the model, which unfortunately cast some doubt on really what's going on. So, for example, it worked well only in certain kinematic regimes of describing the strong interactions. And it also had the embarrassing feature of predicting particles that were not observed. For example, it kept predicting a massless particle with spin 2, which was not observed in the spectrum of the hadrons. Another apparent bug is that it only works in dimensions which are greater than 4. So these would appear to be problems, I hope you would agree. And where to go next was one of the questions. Let me just, before we go on, let me explain how one of the bugs appears. So you might start by studying an open string as a model of a quark-antiquark pair, a meson. The problem is that dynamically it is possible that the ends of the string might join together, and you go from having an open string, which describes things which you actually like in the spectrum, to a closed string. And it's the closed strings, which Melanie perhaps told you today, or at least alluded to, I hope, that carries that spin 2 massless particle. And so even if you started with a theory containing open strings, you will generate, because of this process, a massless spin 2 particle, which isn't in the spectrum. So that's apparently a major bug of the theory. It's certainly a major bug of the theory if you are trying to describe the strong interactions. Anyway, particle physics grew up, and gauge theory arrived. Now, those of you who are on the lecture courses know that gauge theory, there's a lot of structure to it. It's very beautiful, and I'm certainly not going to describe all of gauge theory to you here. But let's try and get at the essence of the kind of tool that you need. But let me just remind you, although you know this, let me just remind you of some of the essential concepts which are embodied in quantum mechanics. So, quantum mechanics. I'm trying to get something to go from A to B. Okay? I'm trying to describe that in my physical theory. How do I compute the required trajectory? Well, as you know, one way of formulating it is with something called an action principle. I form this combination here, which is the Lagrangian, or Lagrangian density. I integrate over the elapsed time between A and B, and I have this quantity called S. And the point is that I can extremize S. I can, for example, require that it be a minimum. That quantity for the path going between A and B, I can compute that quantity. That's the kinetic energy. That's the potential energy. And if classical mechanics that we know, Newton's laws of motion, etc., arise when I ask that S is a maximum or a minimum. Let's actually try and unpack what is the important thing. Just a little bit of a dimensional analysis that I want to get at here. Let's just actually compute the trajectory in a small time, delta t. Let's look at a little piece of the trajectory. There's the brick, or whatever it is we're studying. It's moving with velocity v, and so the amount of distance it moves in time delta t is x. And the action, if you go and put it in, looks like this. You can see the mv squared of the kinetic energy. I'm integrating over time, so that brings in a piece of time, a delta t. But you can see that this has the dimensions of a position, and this has the dimensions of a momentum. So the actual dimensions of S, the action, is x times p. Quantum effects, things that we call quantum mechanics, quantum mechanics becomes important because nature has given us a basic unit of action. It gives us a basic unit which has the dimensions that I just talked about. And it's 1.05 times 10 to the minus 35 kilograms meter squared per second. And so it's obviously a very, very small quantity, and that's why we only noticed it in the 20th century. Physics is very different when the actions that you're studying are, in some sense, close in size to h bar. And that's a quantity, Planck's constant. So let's actually reformulate things in terms of quantum mechanics. You've probably seen this. So the point is that when I study motion from A to B, quantum theory says that I actually have to consider all possible paths that it can possibly take, and they actually contribute significantly. And I formulate quantum mechanics by saying, if I wish to evaluate the result of some motion from A to B, I sum over all paths, and I weight each path by its action according to this factor. You can see that I'm raising it to a number because S and h bar have the same dimension. So it makes sense to do that. When everything is much larger than h bar, actually this reduces to the standard prescription that I described before, and I believe, for those of you in the lecture course, Douglas Smith probably told you a little bit about this, or actually a lot about it. So let's actually just think about what h bar actually is. So I have a little series of boxes here to tell you that. In some sense, it's a measure of the uncertainty in a particle's position and momentum. The idea is that I have some uncertainty, delta x, in the particle's position, where it is, some uncertainty in the position, in the momentum of the particle, and nature actually tells us that this is true. There's a natural length scale. There's a natural length scale I'll allude to shortly, which arises from that. So that's Heisenberg's uncertainty principle, and somehow that's one way of thinking about that's another way of thinking about what h bar actually is. Here's another way of thinking about it. For the more mathematically minded, you can study that formula. Let's not worry about it. Another way of thinking about it is that there is a natural length scale that a particle of mass m has. And it's called the Compton wavelength. So a particle of mass m, anything, mass m, and I can compute the Compton wavelength by using two fundamental constants that nature has given us, c and h bar. Okay? If you try and localize the particle inside its Compton wavelength, then there's an uncertainty in its energy, which is about E equals mc squared. And so in some sense, that's one way of thinking about where the Compton wavelength comes. When you have a particle has mass m, I can exchange that for an energy equals mc squared. That's where the c comes in. And if I try and trade that for an so I get to worry about just how accurately I can locate the particle or say what its energy is, and that translates into how much I can squeeze the particle inside its own Compton wavelength. So most things actually, when m is big, you can see that that's an extremely small number, and that's why we've never had to worry about it before the 20th century. You know all of this, but it's useful to just review some of these things, because it is sort of nice. So what do we do? What does gauge theory do? What does particle physics do? They don't worry about strings. They ask a question. Here's an electron, here's another electron. They interact somehow, and then they go back out. And you ask the question, what happened? Maybe something like this or some other kind of thing. And you can imagine what goes on, but actually gauge theory gives you a precise tool for actually computing how that works. And you've seen some of this in the lectures. So, for example, here is that electron, and here is the other electron, and they interact by the electromagnetic force, and that interaction is mediated by a messenger particle called the photon, and you get to draw a diagram like that. The theory of quantum electrodynamics supplies you with a precise number representing this diagram, and a precise number representing this diagram. And it gives you a basic rule. It says, as long as I make all diagrams that out of this particular vertex, and then I have a number associated with this vertex and a number associated with the propagators, as you know, I can compute everything, and I just go and I calculate. And that, as far as I'm concerned, is our definition, our working definition of what gauge theory is. It's a rule for giving you a set of vertices between, interacting between messenger particles and matter particles, if you like. The point is that the idea of quantum mechanics, summing over all paths, is encoded in this as well. So here is the electron going out, one electron coming in and going out, here's one going in and coming out, and this is one possibility for what could have happened, but I must sum over all paths. So another possibility is that the photon splits on the way into an electron-positron pair, which then annihilate and convert themselves back into a photon, and then interact with the guy going out. Okay, so you must sum over all of those possibilities in order to understand how to compute something, And so that is, as far as we're concerned, what gauge theory really is. It's a set of rules for implementing the idea of quantum mechanics that we saw on the previous slides. And as you know, sorry, just waiting for my slow rendering to render. As you know, there is a wonderful thing called the Standard Model summarizing all of the properties of particles that we know about. This, of course, I'm not expecting you to read, but I have some snapshots. So these are taken from that table. So we can model the fundamental forces, all of them, almost, using gauge field theories. So we have electromagnetism, and its gauge particle is the photon. We have we have the weak interactions, and we have the W's and the Z. And these guys are unified, as you've heard from Professor Martin, into the electroweak theory. I have the strong interactions, and I have the massless gluons, and 8 of those. And then I have that matter is made up of all of these things called the fermions. I have the electron neutrino, I have the up and down quark, and I have various charge assignments, electric charge assignments. And one of the very interesting things about particle physics, which is completely unexplained in the context of the Standard Model, is that you have an identical family in terms of the charges. They're just considerably heavier. So it's as though there's a sort of repeat of what this family of particles here gets repeated here, and then it gets repeated again. There are 3 families which are essentially the same, except they're a bit heavier. That should remind you of something. That should remind you of perhaps something repeating itself, perhaps a musical instrument. You play 8 notes, that's a family of notes on the standard Western scale. And then it starts repeating itself again, talking about whole notes. Okay, and you get the same notes all over again, but they're at higher energy, higher frequency. And then it keeps going. That's very interesting, and perhaps that's suggestive of an idea. But the Standard Model itself can't say anything about that. It just observes these things and then tells you how they interact using gauge theory technology. So this is another table, properties of the interaction. But notice, we have gravitational in this table as well, and it says graviton not yet observed. And, this is something you've heard many times. The Standard Model is absolutely wonderful, but gravity does not fit. It can't be modeled as a gauge theory like the other forces. So you might say, who cares? But actually, maybe this is the biggest problem of all for the following reasons. But before we get entirely to the reasons, let's actually remind ourselves how we think about gravity. So the physics of medium-sized everyday objects is an approximation. I also said this earlier when I talked about quantum mechanics. The physics of medium-sized, everyday objects is an approximation. We don't need to worry about this underlying quantum structure, but we know it's secretly an approximation to it because everything's much bigger than its Compton wavelength. Same thing can be said about gravity. So what do? Well, we worry about the force exerted by one massive thing on another massive thing, and we all write down, what do we write down? We all write down something like that. We have a mathematical thing we write which says, let's assign mass m to this, mass m to that, distance r, that's the force between them. And that's the force law. We put this into our classical mechanics machine, and we can put men and women on the moon, and maybe even on Mars one day. We don't need to worry about other things. But let's actually, just for fun, reformulate it. The reformulation that Einstein told us about says, well, mass, or energy, deforms the geometry of space-time itself. So here's a little cartoon of that thing, that statement. And the idea is that, so I have some heavy mass or lump of energy that has deformed space-time. Think of this as a rubber sheet that got deformed. And particles just carry on following what they consider to be the straightest paths from A to B. And so far away, the straightest path is what we would think of as just an undeviated trajectory. But actually, near the deviation, near the depression, you can see that the straightest path actually might look rather like, for example, if we look at it from above, whatever that means, it looks kind of like a bending of the trajectory. And we think of that as the force of gravity. It gives us the same thing, but then it gives us a whole lot more. And that is, of course, what Einstein told us about. I want to just observe one thing here. Newton told us that nature actually had a very specific constant. So now we have another important constant of nature, which is called Newton's constant, G. And Einstein's equations, which you may have seen, can be written like this. I just gathered everything that describes geometry. You may have seen it in terms of r mu nu minus a half g mu nu r. I've just called all of that big G mu nu for simplicity. Call that the Einstein Tensor. That's what people do. So it just describes geometry. It describes that bending of the sheet that we talked about. And the mass energy that we talked about that creates the bending is in this thing here. And that's all you need to know about Einstein's equations, except that, of course, G, Newton's constant, tells us how much a given mass energy produces some curvature. G is an extremely small number. And so, as you've heard, this actually famously makes gravity extremely weak compared to the other forces. And you've all seen the demonstration of gravity's weakness compared to the other forces. That's one demonstration. Okay, this isn't falling through my fingers essentially because of electromagnetism, but the entire Earth is pulling down on this thing, and I'm beating the Earth trivially, and somewhat embarrassingly for the Earth, by its gravitational strength, beating its gravitational strength. So it's because of that 10 to the minus 11, essentially. So that's one of the reasons why particle physicists often don't really worry about gravity. Anyway, just in the same way that we saw quantum mechanics, there's a natural length scale associated with wondering when quantum mechanics is important. We saw that was the Compton wavelength. If you give me the mass of the thing, I can tell you when you need to worry about quantum effects, okay, by using two constants of nature, h bar and c. In the same way, if you give me the mass of something or the energy content, I can tell you when you actually need to worry about gravitational effects, general relativistic effects. Einstein, worrying about what Einstein taught us. And it uses c again and this new constant of nature we've been discussing. And that's called the Schwarzschild radius or the Schwarzschild length. And so how does that work? Well, it's the scale at which general relativistic effects can't be ignored. And the idea is that if you compress something, for example, you compress something inside its Schwarzschild radius, you'll have a set of effects which cannot be described by Newtonian gravity, and you need to worry about Einstein. You need to include what Einstein taught us. So we have two length scales. Actually, now I can answer the question that's been on your minds. I kept saying medium-sized. Now I can actually tell you what medium-sized means in precise terms. I said medium-sized objects don't need to worry about quantum effects, and medium-sized objects don't need to worry about general relativity. Now I can actually state it precisely. Quantum mechanics is important when the Compton wavelength is larger than what am I trying to say? Yes, is larger than the, if you like, gravitational length scale, and the other way around for general relativistic effects. And somewhere in between, so we have electrons and things, we have stars and galaxies and the entire universe, and somewhere in between is that thing we think of as medium-sized objects, which we normally deal with, and we never needed to worry about other objects before the 20th century. In fact, this is the most natural way of understanding what people are babbling on about when they say, what is the Planck length? When they talk about the Planck length. The point is, what if the Compton wavelength and the Schwarzschild length are actually comparable? Well, we could do a quick calculation. Let's actually set them equal to each other. Here are the two formulae, so we can do it in our notebooks. There's our notebook. And so we equate the Compton wavelength to the Schwarzschild, what have you, Schwarzschild length. We find it a little hard to read, so we change pens. And that defines a specific mass, given that all the others are constants. And there it is. So there's a specific mass. It actually turns out to be 10 to the minus 8 kilograms. And you can ask, at what length does that happen? And that's about 10 to the minus 35 meters. So that's the famous 10 to the minus 33 centimeters people often talk about when they talk about the Planck scale. And the Planck mass is 10 to the minus 8 kilograms. So that's an incredibly tiny length scale. And so that's why people say, oh, it's very inaccessible and what have you. And you might be puzzled, because actually this isn't that small a mass, really. Actually, the Planck mass is about the mass of bacterium or something. So you might ask, why don't I need to worry about quantum gravity effects when I'm doing biology? And the reason is because although a typical bacterium, being 10 to the minus 8 kilograms, is about a Planck mass, it is way bigger than its Planck length, so we don't need to worry about quantum gravity effects for bacteria. But it is interesting to note that the Planck mass isn't some weird, stupidly large number or something like that. Okay. So, I said that. So where do we go from here? Well, let's actually ask ourselves perhaps a deeper question. One of the things we might be worried about is that quantum mechanics tells us that all of the objects in our game that we're studying the quantum theory of, they tend to move and they can change and they can do all kinds of things. They can follow. Basically, all these different trajectories are important, which are important, and they're weighted by some exponentiated action. The point is that Einstein told us that gravity is, in fact, the dynamics of the entire arena in which we live, space-time. So if we start worrying about quantum gravity, we must accept the idea, or at least try and come to terms with the idea, that the arena itself is quantum mechanical. Now, actually, people study the arena, the universe in which we live, They study it all the time. That's what cosmology is in some sense. Well, in an exact sense, right? And they actually worry about the arena changing in a very classical way. And then they do quantum mechanics on top of that. So the really sophisticated cosmologists do worry about full-scale quantum mechanical particle physics. But the background, this blob representing the actual universe, is still classical in their minds. Somehow, we need to go further than that, and probably to address some of the issues in modern cosmology, we need to worry about things like this. The arena itself is fluctuating and changing in a quantum mechanical way. And that's what quantum gravity is supposed to be able to tell us about. So that's why perhaps we can't ignore the fact that we can't quantize gravity. For another example is this. Well, we run the lifetime of the universe backwards. We know that if we extrapolate backwards in time, the universe gets smaller and smaller and smaller and smaller, higher and higher and higher energy density. And ultimately, somewhere around here, we start having to worry about Planck Scale physics. And somehow, that Planck Scale physics, that quantum gravity that we've been ignoring, is going to affect everything out here. And so we do need to understand something about quantum gravity. And actually, if you worry about it, if you think about it a little bit, well, actually a lot, but somewhat, remember with some of the things you learned in Don Marol's course, you know that actually quantum physics is very important in the context of black holes. And in fact, we now know, or we're now very close to 100% certain, that black holes aren't just these crazy things that live in somebody's notebook. They're probably very, very common things, and that actually at the core of most galaxies, there's probably a black hole. So somehow, actually, we can't get away from the fact that our universe must worry about quantum gravity. So why am I telling you all of this? Well, this is where strings come in. So strings return, but perhaps in a different way. So string theory. Well, let's review some of the things we already said. Supposedly, if we look closely enough at a particle with an appropriate magnifying glass, we see that it's really a string. And as you know, the different vibrations of the string are supposed to represent all of the elementary particles, and that's the simple sort of high school idea, which is extraordinarily powerful. And you might ask, what does magnifying glass mean? Well, it means very high energy, more properly, very high energy density, and as we've discussed, and very tiny scales, or equivalently very tiny scales. So, the rules of string theory are not so different from the rules of quantum mechanics in the guise of gauge theory. Instead of the propagator that you would have in your Feynman diagrams, those diagrams we were using to keep track of the interactions before, you have a propagator that looks like this. You have a tube because you have a point moving, sweeping out what's called a world line. Instead, you have, for example, a closed string. That little loop moves and sweeps out a tube, and that thing is called a world sheet. So you can actually see these guys interact. Here are two guys coming in. They interact by doing something like that. You can think of it in various ways as either an exchange of a closed string or joining to form a single closed string. Imagine cutting it across like that. You see a single closed string, and then splitting again to go out to form another closed string. And there are all sorts of diagrams you can draw. There's a sort of fundamental vertex. In fact, there is only one vertex, as opposed to the many that you get in field theory. And you can actually build up string theory that way. So as far as I'm concerned, that is the technology of string theory. But wait, there may be more. One of the things you've heard about string theory is this business of extra dimensions. How to think about that? Well, here is something that's one-dimensional, a line. And supposedly, if I look closely enough at it, I can see that, in fact, there's a hidden dimension. And maybe our universe has extra dimensions, perhaps 6 or 7, because, as Melanie probably told you earlier today, string theory, consistent string theories, seem to like to live in 10 dimensions. And this 7, I will mention what that means shortly. So you've seen all of that. So here's a little catalogue of the various superstring theories that people studied in the 80s after some excitement called the first superstring revolution. When the dust settled, we realized that nature gave us perhaps nature gave us 5 string theories. And they go by various names: type 2A, type 2B, heterotic with a gauge group E8 cross E8, and heterotic with a gauge group SO32, and type 1 with a gauge group SO32. Don't worry about the details, just think that there are 5 different string theories. So this, remember, 10 higher dimensions was a bug when we tried to apply the string theories to the strong interactions, but now it becomes a feature of the theory. Because supposedly, the idea is we live in 4 dimensions, and then the other 6 dimensions are hidden away in some tiny manifold called a Calabi-Yau space, often. And we live in this 4-dimensional space here. So this times means at every point in 4 dimensions, there's a hidden compact manifold. Just in the same way on this stick, if you look at it far away, it's just a line. Then you actually see that it sort of has a cylindrical surface. You can say at every point on the surface, I can go round in a circle. So at every point, there's a hidden circle. So I could describe the geometry of this, the topology of this stick, as a line times a circle. Same idea. So actually, this turns out to be extraordinarily powerful and very successful. So there are actually unexplained patterns in the standard model, for example, which when you try and make models of the standard model using string theory, you compactify down to, on this thing, down to 4 dimensions. What you end up with is a spectrum of particles, which are supposed to be our real world, and you find that aspects of the spectrum, you have a spectrum of particles, and then it repeats at higher mass, and then it repeats, and it repeats. And that should remind you of what I talked about in that table of the particles we've actually observed. And so you can actually get, out of string theory, an explanation for something that the standard model in itself can't explain, it can only describe. And that's very exciting. That sort of comes about because string theories can do things that particle theories can't do. For example, if I look, so imagine our 4-dimensional world is that long line. Here are 2 particles. And the origin of those 2 particles, when you have extra dimensions to play with, can be very different. And that's very important. So if I blow up this and remember and discover that it's actually a tube, you can see, for example, that one of those particles could actually have come from being just a string, which I didn't look at closely enough to see that it was a particle, or it could have been a string that was actually wrapped around the internal dimensions. And it's that ability of the strings to wrap around the internal dimensions and sort of feel what's going on in those internal dimensions that translate into the properties of the standard model of particle physics that you can't explain using particle theory alone. And that's very exciting. And that's one of the promises of string theory, the fact that geometry and topology go together hand in hand to explain various numbers and features of the standard model which are hard to explain. Of course, if we'd solved all of the problems, we probably wouldn't be here because we'd have fixed everything and we'd be at home on the beach or something like that. So obviously there's still more to do. There are difficulties. Not enough is known about the dynamics of string theory for actually choosing which of these Calabi-Yau manifolds nature actually chose. You can come up with nice models of things that look a lot like nature, but aren't really nature. And even if you did find it, you could argue that you needed to come up with some explanation. After all, if I just translate the properties of the standard model into the properties of some internal manifold, I've just redecorated the unknowns in terms of new language. So as physicists, you should be wary when people tell you exactly what we've achieved. We may just have retranslated. So it turns out that strings are just part of the story. When people started trying to worry about just the things I talked about, what are the dynamical principles that pick one Calabi-Yau manifold, one internal space over another, so that you just sort of start in an empty universe with a string theory, or no, you just start with a string theory and you get a universe with exactly the right spectrum of things being the standard model. No one knows how to do that. And trying to find the technology to do that and describe quantum gravity and all of those things together led people to worry about the fact that we'd never really addressed the technology of string theory fully. We can describe a string from over there coming and passing near a string from over there, passing each other and interacting, sort of weakly interacting with each other. But we don't really have much in the way of technology for describing strings when they interact strongly. And it turns out that to answer the questions that I just alluded to, you need to understand how strings interact with each other strongly. And it was in doing that that we realized that there's much more than just strings going on in the story of fundamental physics. It turns out that you always, and people did, you could always ask the question, well, okay, so I was studying particles and now you tell me to study strings. Okay, so I tear up my notebook and I study strings for a while. But why couldn't I have then torn up my notebook and studied membranes? Where does it all stop? Do I go further than that? And people said, well, no, don't be silly. Strings are very special, blah, 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 blah. Well, the answer now we know is yes. We should have done that, and people did try, but they found it very difficult, and they had lots of people laughing at them and things like that. But it actually turned out that they had the last laugh because high-dimensional extended objects, i.e. not just strings, but membranes and things with even more dimensions to them, have emerged as vital to the understanding of the full structure of the theory. And these things are called branes. And there's a piece of language people use, so a particle is called a zero brane. The idea is you have a membrane, so you lop off the mem and you just keep brane, and then instead of mem you have two, because it has two extended dimensions, so you have a two brane. And then a string is a one brane, and a particle is a zero brane. Then you have three branes, and of course if you have 10 dimensions you can go up to a 9 brane, because remember you have 9 spatial dimensions and then it must move. So it turns out that there was a very powerful description of branes that was discovered, which enabled these things to be studied where perhaps others had failed to study them successfully or usefully before. And in a special regime, you can describe branes as things called D-branes, and they're described simply as hypersurfaces where strings can end. So you have closed strings with no ends, and you simply define the extended object called a brane to be the place where strings are allowed to have ends. So you can start with a closed string theory and simply ask that that a brane be in the theory, an extended object, a fully dynamical extended object, and you define it by simply saying there's a hypersurface there where strings can end. And you don't need anything more than your knowledge of how closed and open strings behave in order to then intrinsically define the behavior of this blue thing. And that's essentially the tool. And that is incredibly powerful, it turns out. Now notice something here. Gravity, as I said before, is carried by closed strings. And these guys are not on branes, whereas open strings have their ends trapped on the brane. That's an important thing, which we will get to later on. Branes can actually end on other branes, but that's beyond what we have time to describe. That's a good question. So D-brains turn out to be incredibly powerful tools, and I just taken some snapshots from my notebook of things you can do with brains. So, for example, there is a brain, this blue thing, and you can get it to emit a closed string by, well, you can see the diagram, you can think about it. You can actually have one brain, which is this red thing, and the two brain, this blue thing, interact with each other via the strings which interconnect them, and you can connect the brains up into all kinds of amusing shapes. It's a lot of fun, and all of this technology triggered what's called the second superstring revolution, or I should say fueled the second superstring revolution, and led us to a fascinating picture, because it turned out that those were the tools you needed to describe strings when they interact with each other strongly. And so, I don't have time to tell you the whole story, but what actually happened at strong coupling is that we learned that, in fact, by studying strings just in terms of their weakly coupled regime, we missed the fact that they're actually all part of the same theory. They all fit together in a very beautiful way into a bigger puzzle, which is believed to be a complete theory, and that complete theory is called M-theory. Notice that in addition to the 5, 1, 2, 3, 4, 5 string theories, there is also something that lives in 11 dimensions, it turns out. And so actually somehow, not only do we learn that the dimension of that strings, the different strings can merge into each other when we work at strong coupling, but the dimension of space-time itself can change from 10 to 11. There's all kinds of weird things which you get to describe when you study extended objects. In fact, you can see roughly where that 11th dimension comes from. Here's a string weakly interacting, so there it is, and then it might split and form two strings. And so the string coupling at some dimensionless number called G strings, much less than 1. At strong coupling, what actually happens is that you discover that there is a circle, a hidden extra dimension that you didn't know about before, and the string itself came about because it was a membrane which was kind of tangled up on that circle. So if you kind of imagine this is a two-dimensional membrane forming a sort of tempting deformed donut-like shape, imagine shrinking the cross-section of that down, at the same time losing that cross-section is wrapped around the hidden 11th dimension. As that dimension disappears, you get down to 10 dimensions and a string. And so in some sense, that's the way of seeing that dynamically the dimension of space-time can change as well. Okay. So, thus enriched, string theory actually gets also to return to its roots. So, there's much to do, as I said, in thinking of string theory as a theory of everything. I just reminded you of some of the successes of it. I told you what happened in what's called the second superstring revolution. But ironically, recent research has also shown that string theory, it wasn't actually necessarily wrong to study string theory as a theory of the strong interactions back in the 60s. That actually may not have been too far from the truth as well. I don't have time to explain all of this picture, but let me sort of quickly get you to think about what the various things mean. This big green shell, think of the surface of that shell as our four-dimensional space-time in which we live. But actually, it's just the boundary of a five-dimensional ball which has an interior, that yellow stuff. And actually, it turns out then that the mesons in our world can be successfully modeled as the endpoints of strings, which, just as we had said very early on, those are the endpoints of the string, but they kind of stretch deeply into the interior. There's also a hidden phi sphere I haven't described. So this space, this is a model of that sort of thing. Oh, and baryons as well. You may always have worried when people say, oh, and maybe we can model strong interactions with, mesons, quark, anti-quark, and then you go, what about baryons? They're made of 3 quarks. A string can't have 3 ends. Okay, well, that's how you get round it. The ends of the string start here, 3 different strings, and they go off and end on something which is in fact wrapped on a hidden 5-sphere in the hidden dimensions. So that bug, those hidden dimensions, play a nice role. They allow strings to get new properties by being able to bend into the hidden dimensions. And the bug resurrects itself as a feature, which is awfully nice. The model of this is space-time called ADS, anti-de Sitter. Actually, you may wonder what anti-de Sitter is. Here's a picture of anti-de Sitter, or in lower dimensions than the 5 I just showed you. The reason I show you this cartoon, this drawing, which you hopefully recognize, is because this is, in fact, a well-defined mathematical space that has a well-defined there is a well-defined sense in which going from here out to here is going out to infinity, but is somehow, in another sense, still a finite distance away. There's a finite, well-defined boundary. You can see that somehow the scale of the metric that you use to measure things changes in such a way as to achieve that. This is also, of course, a drawing of M.C. Escher. There's another one. Anyway, blah, blah, blah. So this is kind of a 5-dimensional version of that. That's one way of thinking about what anti-de Sitter is. Okay, I'm almost done. We actually have to catch the bus to the observatory at 6:10, so I should finish on time. I'm not going to. I'm going to take 2 extra minutes. There's another important idea which this technology that I just described to you allows us to make contact with. Perhaps that whole picture of string theory lives in 10 dimensions, you curl up 6 of the dimensions, or perhaps 7 now, into a little ball, and then you have the 4 dimensions remaining. Maybe that isn't the way nature chose to use string theory. Here's another way. And one of you, actually, in questions in either the first or the second lecture of Melanie's, actually stumbled on this idea without actually realizing it, which is very impressive. See what you can do when, you think. Okay, so many people are working furiously on this idea. Maybe the idea is that you have 10 dimensions. All of this light blue is 10-dimensional space-time in which string theory, or maybe it's 11-dimensional in which M theory lives. If M theory is 11-dimensional, maybe M theory doesn't have any dimensions at all. That's another story. Perhaps our universe is just itself a 4-dimensional, 3 plus 1-dimensional brain, just sort of suspended in that universe, which is in fact really the larger universe, which is much larger in dimension. What you need, of course, is some mechanism by which the 4 forces, do what they should do. So the gauge forces, the forces which are naturally described by open strings, live here and somehow can't get off. And that's the stuff we're made of. And that's why we don't know there's these extra dimensions. We don't need to curl them up because we can't get off to see them. And that naturally fits that picture I showed you with the ends of strings defining what a brain is. The ends of strings with ends describe the fundamental gauge forces. And then closed strings, remember, could get off the brain and wander around wherever they liked. So the closed strings, which carry gravity, that spin 2 guy, can wander around in the higher dimensions. But that's great, because that also gives you a nice mechanism for maybe why gravity is so much weaker than all the other forces. Because if you think of the flux line pictures we were drawing, the flux lines, when I separate 2 things in this brain, say 2 electrons, the flux lines get to stay trapped. They stay trapped in the 4 dimensions because they're only a 4-dimensional force. And so they don't spread out so much, so the force doesn't dilute so quickly. Whereas if I was studying the gravitational interaction between 2 things, either both on the brain or one on the brain and one out there, the flux lines leak into all the 10 dimensions. They get dilute much faster. So maybe that's why gravity is so much weaker. That's also geometry. So that's a beautiful idea that people are working on as well. So that's these scenarios go under the names large extra dimensions, brain worlds, etc. And so these are active ideas that people are working on using very powerful mathematics, very powerful physics ideas. Maybe that will ultimately tell us that, yes, strings are in everything and everything's made of strings, Probably not. Maybe not. But what we do know, as I said before, is that extended objects, these mathematical things which are higher dimensional, may be physical as well and may have a role to play. Or perhaps none of them are fundamental. Maybe there's another level to the story that we haven't yet learned to describe. But anyway, that's an overview of some of the things that you've seen all working together. Thank you.